So remember that we have introduced what is called the linear momentum, and the linear momentum is the vector p, and it's simply mass times the velocity vector. So in French we call this linear momentum quantité de mouvement. So it's now time to have a new notion of angular momentum, which we will call the vector L. And the vector L is the cross product of the position vector with the linear momentum. So in French it's called moment de la quantité de mouvement or moment cinétique. Yeah? So the angular momentum depends on the choice that you've made on the origin. Okay, so strictly speaking, we should be saying angular momentum relative to O, where O is the origin of your reference frame. So we have defined the angular momentum, and now we can have a look at the time derivative of the angular momentum. So we have to take the derivative of this quantity, and you will have two terms. Okay, so first you take the derivative of this one, cross product with the linear momentum. So the derivative of the position vector gives you the velocity vector, cross product with the linear momentum. But this thing here, as you're taking a cross product and you have the angle between this one and this one being 0, right? And you know that the cross product is proportional to the sine of the angle. Well, we see that you can cross out this one because it will give a 0 contribution. The second term that will be appearing is the position vector r cross product with the derivative of this one, and this gives you this contribution here. So position vector cross product with mass times acceleration vector, and we know from the second law of Newton that this is the net force acting on the mass. So we obtain this quantity here, and this we know that it's the net torque that is applied on the particle around the origin in your reference frame. So the time derivative of L, the angular momentum, is equal to the net torque that is applied. Well, we have just seen that the time derivative of the angular momentum is the net torque that is applied around the origin of your reference frame, right? So this is the rotational equivalent of the second law of Newton, which states that the time derivative of the linear momentum is equal to the net force that is applied. Okay, so this is why this equation here is often called the rotational form of Newton's second law. Remember that L, the angular momentum, is a vector. It's the position vector cross product with the linear momentum. So if you take your right hand and you have your thumb pointing out the screen, you will see that this is actually the direction of the angular momentum, because the natural movement of the fingers is the one that goes from R to P, right? So the angular momentum points out of this page, out of the screen. Okay, suppose that you have no net torque applied, then you have the time derivative of the angular momentum is 0, which means that the angular momentum is preserved. Okay, and so you have something similar for the linear momentum. If you have no net force applied, this means that the linear momentum is preserved. Well, let us now apply this to planar circular motion of an elementary mass. Okay, so the mass is over here, and it's moving in a circle of radius r, so the distance here is from the origin is r at an angular speed of omega, right? So the angular velocity vector is omega with an arrow on top, and it is sticking out of your screen. The speed of the particle, okay, which is the magnitude of this velocity vector, is r times omega. So this is the velocity vector, and this is the position vector. You remember that the angular momentum, well, here it is, it's a vector. It's also sticking out of the screen. Well, it's the cross product of the position vector and the linear momentum. The linear momentum is mass times this velocity vector, right? So, as I've said, you take the cross product of this one with something in this direction times m. Well, the result will be something that is sticking out of the page. You just take your right hand, you take your thumb and you point it out of the screen, and you will see that the natural curl of the fingers is a rotation from r to v. So the angular momentum L is sticking out of the page. So you know that the magnitude will of course be proportional to m, right? It will be proportional to r, so that explains one of the r's, and the magnitude of the velocity vector is r times omega. So you have again times r, which explains the r squared here, and then you have omega in the direction pointing out of the screen, and this is exactly the angular velocity vector. So one way to write this is that the angular momentum is something that is over here, and this is what we'll call a moment of inertia. This is the moment of inertia of an elementary mass around the center, and we'll call it Jz. Nothing to do with music, and it's pointing out in the z direction, yeah. And so you have Jz times the angular velocity vector. So you obtain, if you take the derivative, the very familiar form of the rotational form of Newton's second law. So if you take the derivative of this one here, okay, we know that it's equal to the net torque that is applied around the center here, and we'll have to take the derivative of this one, so that's Jz, the moment of inertia for a rotation around the z axis, right? And if you take the derivative of this one here, you'll have the acceleration vector in rotation. And so we obtained this form that you know very well. Well, we've just seen that the time derivative of the angular moment is equal to the net torque that is applied, and it's equal to the moment of inertia. Okay, well, it's along the axis of rotation, and in the previous example it was z, but let's just note it as j, times the angular acceleration vector. Okay, and now let us assume that there is no net torque applied, so this one is 0. So this means that this thing here is equal to 0, and this means then that J, the moment of inertia, times the angular speed is a constant, right? This is a scalar equation, right? You have to remember that this thing here points in the direction of the axis of rotation. So what will happen if we increase the moment of inertia? We can increase the moment of inertia by making sure that there is more mass far away from the axis of rotation. As this thing here is constant, this means that the angular speed will go down. If we decrease the moment of inertia, this means that we bring more mass close to the axis of rotation, then we'll have that the angular speed will be increasing. Well, I found a little video that is illustrating this conservation of angular moment.
Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases.
Well, we have a similar result, of course, for linear momentum. Remember that the variation of the linear momentum is equal to mass times the acceleration vector, and this is the net force that is being applied, right? This is Newton's second law. Well, let us suppose that the net force applied is equal to 0. This means that mass times acceleration is 0, but also that m times v, that's the magnitude of the linear momentum, is equal to a constant. Okay, so if we can somehow influence m, we increase it, well, the speed will decrease, and if we can increase m, the speed will decrease. I found this nice little video that is illustrating the law of conservation of linear momentum. Well, I will now start talking a little bit about energy. So suppose that you have an external force here that is acting on a mass m, and this force is making this mass m going from a point 1 to a point 2. Okay, well, the work done by this force is this integral here. Remember that work is force times displacement. Indeed, you have the scalar product of the force vector times the displacement vector, right? So this displacement vector you can write as the velocity vector times dt. We know from Newton's second law that force is mass times acceleration vector, or stated otherwise, mass times the derivative of the velocity vector. So if we stick these in this one, this is what you obtain. So this is a scalar product. So it will have magnitude dv dt times v. Okay, and this can be seen as the derivative of v square over time. Okay, and this is what you're seeing here. And of course I have to put a factor a half in front, right? So we obtain now this quantity, and if you compute that integral, this is what you obtain. Okay, the work that is done by this force is equal to this thing here, and it's a difference. It's a difference between this term here, okay, m over 2 times v2 squared, and you have something similar, okay, m over 2 v1 squared, and I assume you recognize that this is the kinetic energy K2, right? Kinetic energy is the energy that can be written as mv squared over 2, and it's of course a scalar quantity. So the work done by the force acting on the particle in going from point 1 to point 2 is related to the difference K2 minus K1. Well, you probably remember from previous courses that some forces are said to be conservative, right? This means that the work that is done in going from a point 1 to a point 2 over different trajectories, for instance, that's one trajectory, that's another trajectory, that's yet another trajectory. Well, if the force is conservative, then the work that is done in going from 1 to 2 will be the same whatever the trajectory. Another way to state this is that the work done on a closed path, okay, this is a closed path, is 0. So a force or a system is conservative if there is no friction and there cannot be any dissipation forces. A necessary and sufficient condition for a system to be conservative is that the force field derives from a potential. So the force field can be written as the gradient, yeah, minus the gradient of a function u, which is called the potential or potential energy. Okay, so we know that for conservative systems the work is independent of the path of integration, so it's kind of logical that the work depends only on the endpoints and on the potential at the endpoints. This is why you can write the work like this. So it's the potential in u1 minus the potential in u2. We've seen previously that you could also write the work as K2 minus K1, right? So if you now take this equation and you rewrite it differently, this is what we obtain. Okay, so of course this is true for conservative systems. This means there are no dissipation forces. If this is the case, well, the total energy, this is the kinetic energy, this is the potential energy, is preserved. We have seen that some forces are derived from potential, and then you can write it like this, where u is the potential, right? So Let us take a few examples. The first example is gravitation near Earth. Then you can write the potential function as mgz, and the force that is derived is simply minus mg pointing along this vector here, which is actually pointing towards the center of the Earth, right? This is gravitation near Earth, but in general you have the gravitation, and I mean universal gravitation. There you have also a potential function UR minus G m1 m2 over R. Okay, each time the potential function is a scalar function, and this is the gravitation constant. The force that is related is minus J m1 m2 over R squared, and it's acting along this vector here, which is pointing from one mass to the other, right? Let us take another example that you probably know. A spring. So, spring, potential energy that is stored in the spring depends on the length. When you look at the difference between the length at rest, and we'll call that length x, and it's a half k x squared. So the force that will be derived from that potential function is simply minus k x. This is something that you already know also. There are other examples, but I won't mention it. Well, not at least not in details. Another example of that is electrostatic force between charges. So we can use the equation of conservation of energy to derive the motion of a pendulum. So let's draw the pendulum. So that's the vertical, and so that's the angle phi over here. Okay, and the length of the pendulum is L. And you can kind of see here that this distance over here is L times phi. So you can see that the speed will be V is L times phi dot. Okay, so I will draw the pendulum in 3 positions. So in the blue and green positions, the height is maximum and the speed is 0. Okay, since the speed is L phi dot, and in these positions in blue and green phi is at its maximum, well, phi dot will be 0. So you can see it here in these 2 extreme positions that the potential energy will be maximum and the kinetic energy will be minimum, and you have something similar over here. So the potential energy is maximum and the kinetic energy is minimum. In this central position, the speed is maximum, right? So the potential energy is minimum and the kinetic energy is maximum, right? So you can see that there is an exchange between kinetic and potential energy. So what we can say is that the sum kinetic energy plus potential energy is a constant, right? So the kinetic energy is a half times m times the speed squared, and the speed here is L phi dot, and the potential energy is mgl times 1 minus cosine phi, and that's a constant. You can see here that this term over here will be 0 when phi is equal to 0, and indeed the potential energy will be 0. So the equation of conservation of energy says that, well, the derivative of the sum kinetic plus potential energy is equal to 0. So if we compute this derivative, we have a half times m times L squared times the derivative of phi dot squared, so that's 2 times phi dot times the derivative of phi dot, and that's phi double dot, plus mgl. The 1 will not give a contribution, so we have to take the derivative of minus cosine phi, so that will be sine of phi times the derivative of phi, which is phi dot, and that's equal to 0. So there will be a lot of simplifications over here. We have also the L, so the square will disappear, and the phi dot over here, and we end up with the well-known equation of a pendulum: phi double dot plus j over L sine phi is equal to 0.